Good day, everyone. My name is David Williams, Executive Director of the United States Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Artificial Intelligence in Energy, from Pipe Dream to Practical Applications. We are grateful to our moderator, Dr. Anna Ebers Broughel from Tetra Tech, and our distinguished panelists for today's timely discussion. First, a little bit about the United States Association for Energy Economics. We are the largest affiliate of the International Association for Energy Economics and provide for a forum of the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations along with a host of other products and services you can find at our website at www.usae.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our moderator. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our panelists, please click the Q&A button at the bottom of the Zoom window and type your question. We've allocated sufficient time at the end of the webinar to address your questions. And now I would like to introduce you to our moderator, Dr. Anna Ebers Broughel, economist and statistician at Tetra Tech. Anna, over to you.
Thank you, Dave. Welcome to today's webinar on artificial intelligence and machine learning applications in energy. I'm Anna Ebers Broughel, and I work as an economist at an international engineering consulting firm, Tetra Tech. It's my pleasure and honor to moderate this webinar. Today's topic, artificial intelligence, is as important as ever. Some organizations such as OECD heed AI as the next general purpose technology, comparing it to the invention of the steam engine, electricity, or the internet. And today we'll discuss whether this technology has the potential to deliver on this promise, and we'll showcase several AI applications in energy industry. Another important aim is to show that AI field is ripe for increased involvement by economists, especially behavioral economists and others, and could provide fertile ground for future research. Our first speaker today is Dale Kruchten, who is a Director of Advanced Solutions, Energy Analytics at Guidehouse, also previously known as Navigant. He has several decades of experience with AI and machine learning, and he has pioneered over 250 major advanced analytics solutions for the US utilities. He will provide us with an overview of the history of the AI, the stages of its development, and how the AI applications became not only smarter, but also more trustworthy over time. Our next speaker will be Suzanne Russo. She is the CEO of Pecan Street. In the past, Suzanne was a director of sustainability initiatives at the Department of Housing in New York City. Forbes named her as one of the 5 women who are using technology to blow up social change. She's a mover and a shaker. She will address how AI can help decarbonize the grid and lead to more equitable energy system. Our third speaker, Kristjan Eljand, is a technology scout. What a cool name at Eesti Energia, a publicly held energy company in Estonia. Estonia is often considered as one of the most digitally advanced nations on this planet, which is also true in energy. All Estonian consumers have smart meters, and the country is covered by electric vehicle charging stations. It has also experimented with energy blockchain. Kristjan will share how Eesti Energia implements some of the machine learning and AI technologies in energy. And without further ado, I'd like to hand over the floor to Dale.
Thank you, Anna. And let's see here. There we go. Can everyone see my screen? Just wanted to check. As Anna said, we're going to begin with a brief history of AI, to steal a bit of Stephen Hawking's title, to start to look into how we got to AI today. AI actually in many forms has been around for centuries. Man has tried to mimic man's way of working and thinking in many regards. But it wasn't until the late 60s and early 70s that we first got into really useful applications of it. And these were referred to as rule-based expert systems. Some of you older ones in the audience, like myself, cut their teeth dealing with AI with expert systems. They first made their major inroads in the medical area. This was back in the 1970s. As you can see on the right-hand side, it had some very definite strengths with regards to perception and reasoning, but was incapable of learning and abstracting. So it had some limited capabilities in the sense that it could not automatically grow or become autonomous in any way. Next came machine learning. Some of you may have remembered some of the very first instances of neural nets that came out. The first great entry into this arena of automated machine learning. This was back in the 1980s. The rules that it ultimately produced were encoded in approximately 500 weights. For those of you who are at all familiar with neural nets, you'll know exactly what I'm talking about. For those who aren't, is that the neural net is made up of a number of different weight factors that interact with other values to be able to produce an output. The way the machine works is through these weights. The next major breakthrough was what's referred to as deep learning. These are the ones where a lot of you may have heard of this because this has been relatively new. It came out in the 2010s. This is these deep learning machines that can understand images, that can understand spoken words, can understand text, some really amazing aspects of this. But there's a major problem here. As you can see up at the very beginning, when we go all the way back to the rule-based systems, they could explain themselves in terms of how they got to the answers. The machine learning-based methodologies can't explain themselves. So, be able to get to understanding how we can deal with explanation, we need to understand the differences between these two major forms of AI, machine learning and knowledge representation and rule-based reasoning expert systems. The rule-based is a top-down approach. It's a hypothesis, getting observations, and confirmation. It's a forward reasoning process based on deductive reasoning. The machine learning is a bottom-up process that goes from observations, discovers patterns, and produces a tentative hypothesis. And that word tentative is very important because everybody believes that the output from these machines is absolute, and it is not. It is a probabilistic output. It is uncertain. But by looking at these two methodologies together, if we were to figure out a way of combining them, we can now produce a new form of AI that exhibits the best qualities of both in terms of perception, learning, abstracting, and reasoning. And this is actually the state of AI today. And this actually is a form of AI that I and my team are currently working with at Guidehouse. And this is the reason why it is so important. That suddenly you've got the ability to be very accurate in terms of reasoning and perception as you have, and the learning capability of the deep learning, now combined with the best aspects of the rule-based systems and have the ability to explain their answers. So why is explainability so important? Well, it begins with the user. Any of you who have used an AI-based system, in many times you've gotten answers that you may not have understood. And as a result, there was no way for you to understand how was it that the model came to that answer or came to that conclusion. As a result, this establishes a sense of mistrust in the user, that they can't trust the answers coming out of the new process. So by having an explaining capability, we're focusing on being able to truly answer the questions that are over here on the right-hand side, and in so doing, established a very strong sense of trust in the user of the model. But one last thing I'd like to talk about with regards to AI, and this is a new area for many of you, I'm quite sure, and it's the concept of a digital twin. Kind of an interesting name, but essentially a digital twin is a dynamic digital model of a physical entity, be it either an asset, a process, or even a person. The whole idea is that if you were to then collect real-time data from the physical entity and link it into your digital model, and then also provide feedback from the digital model to the physical entity, you've got a ability for the digital model and the physical entity to come in complete sync with one another. The example I have over here on the right-hand side happens to be one that's kind of near and dear to my heart, and that is creating a digital twin of a wind turbine generator, so that we can understand exactly what state the wind generator is in at any particular point in time. But even more importantly, because the digital twin is a model, we can now project forward the potential states of that physical entity, or in this case, the wind turbine generator, and understand what could possibly happen to it in the future. And this is why the digital twin is AI. It is constantly learning and adapting to its physical twin. It's using the elements of AI to understand exactly what's going on with the physical twin at any point in time, and adapting its own operation and functionality to be in complete sync with the physical twin. This is going to be an important concept very soon, so we're going to come back to this. But now let's focus on why we're here today, and that is talking about AI and energy. What I've got here is a taxonomy of a number of different areas of applying AI to energy. This may even seem a bit complex even right here, but believe me, this is just a mere sample of the areas in which AI impacts energy. And I've only classified this into two areas, classification and prediction, and optimization. Believe me, a true full-blown taxonomy wouldn't fit on a whole number of pages, and we'd be here for hours discussing it. But for right now, let's talk about one specific one, HEM, which stands for Home Energy Management, which may be very near and dear to many of your hearts. As you'll soon see, this seemingly simple concept can be very, very complex. And let's start with it with a view from the grid side of the problem. Looking at it from the grid side, the whole point of managing the grid is to be able to optimize the performance of the grid so that power is distributed to every single customer facility that is needed at any instant in time. This is an incredibly complex problem and involves, in many cases, millions of variables that need to be controlled and manipulated. In many ways, it is not being solved optimally across a lot of utilities. They try to come as close to optimal as possible. But the greatest problem associated with this is having to understand what are the true drivers of all of the complexity with regards to this system. And it comes from this side of the problem, the end users, the customers, in terms of their activities, their behaviors, their decision-making processes with regards to adopting various forms of energy usage and so on and so forth. In order to solve this problem, we need to understand, model, and predict what's going on over here. Otherwise, we have no hope of being able to achieve optimization of the grid. So how do we understand customer energy usage? It begins with realizing that customer energy usage has many different components to it that make it up. The first one can be considered an engineering point of view with regards to the building or structure that they're in, the systems that are within it, the heating and cooling and ventilation systems, lighting systems, so on and so forth. And also the end uses, anything that plugs in. And you can't forget even your battery powered ones because they ultimately need to be plugged in to charge. The next one is economics. Economics comes into play with everything associated with energy because energy costs money. It influences everything in our daily lives. It influences everything in business and commerce. It influences even everything in governmental aspects. So all of these two things need to be taken into conjunction together to be able to have any hope of understanding the customer energy usage. But it doesn't end there. We need to also understand the psychological aspects here because we need to understand how customers end up making decisions. They do not always make rational decisions from an economic point of view or even from taking into account the engineering aspects of it. So understanding what their perceptions are, what their behaviors, what their goals are becomes paramount as well. And lastly, there's a sociological aspect in terms of understanding their activity and more importantly, their interactions. What's their social network look like? There's many different social networks that they have. They have neighbors, they have friends, they have relatives, they interact with the community. Even various forms of communication come into play here. Well, these last three kind of fall under the umbrella of behavioral economics. And we have used behavioral economics extensively in being able to try and both understand and ultimately model the behavior of customers with respect to the usage of energy. But interestingly enough, all four of these fall under the umbrella of artificial intelligence, both in terms of understanding how customers deal with the problem of managing energy usage from all of these different points of view, but more importantly, how to be able to knit them all together so that you have one cohesive view of how the customer chooses to use energy. Next, we have to go on and understand how to model and predict the usage of energy. Well, this is a conceptual diagram of a model that takes into account all of those aspects that I just discussed. You'll see that household dynamics, human activity, groups and networks, organizations, all of the technological, all of them are taken into account in this model. But this model doesn't explain how to do it. It's a thought experiment. So how are we going to move from this thought experiment to an actual model that could model and more importantly be able to predict the behavior of our customers through the use of the digital twin? You literally build a digital twin model of the building and all of its occupants. Now, I'm not going to go through the details of how each of these key elements here labeled in blue works. You're going to have to trust me that AI does in fact work in these areas and that this actually can be done. And I'll give you proof of it very shortly. But the whole point here is that you now have a model that can understand and predict the behaviors, activities, functions, and aspects of a structure that are sensitive to energy or end up impacting energy usage, all in one unified model. And that this model can learn and adapt over time. But why stop at buildings? If you can build a digital twin for a single building, why couldn't you do it for an entire city? And in fact, what you see over here on the left-hand side is an effort that was done by Cambridge University over in the UK. In fact, they're the ones who designed the building digital twin, of building a dynamic city digital twin that literally looks into the management of energy across an entire city. And this over on the right-hand side is just a snapshot of that, where they're looking at a couple of key components of it in terms of understanding the energy of a prosumer. That's the new term that exists today for people who've got the ability to generate their own energy. They're both a consumer and a producer of energy. Smart energy data analytics for a specific area. This is building management. This is the building aspect that came into play. Energy security for the city, so on and so forth. This actually really exists. There's been virtual models, virtual digital twins created for entire cities throughout the world. The one that became the poster child for this was Singapore. You can go on the web right now and go to a website. In fact, it's down here. I have it down here at the bottom, which is the Singapore government. And they have the website that has some really cool videos on it of a system that they call Virtual Singapore. Over here on the left, they use it to determine what buildings would be optimal for installation of rooftop solar panels. Over here on the right, they were using it to determine an optimal bike path through a particular area. But they've upgraded this model to include all of the system utilities. They're including transportation in this. They're including commerce. And the way they made this a digital twin is they've got smart sensors throughout the whole city. They've got cameras that are monitoring traffic. And all of that information in real time is being fed into this whole system so that their digital twin becomes completely in sync with what's going on in the city. And this is an instance of where AI is now directly impacting the economy, the commerce, the operation, function, and well-being of an entire city. Because this digital twin model has the ability to project forward in time various dynamic elements of the city, be it transportation, energy, what have you. And this is what ends up driving economic and urban development for Singapore. So I would strongly urge all of you to go and look at this website. It is quite impressive. But Singapore is not the only one that's doing this. There's cities in Japan that are doing this, Australia, and especially Europe. Berlin and a couple of other cities in Europe are doing this as well. This is the coming true application of AI, going beyond just dealing with solving energy on a customer by customer basis, or solving it from the grid side of the equation. This is solving it on the customer side to a grand scale. Unfortunately, there isn't an example of this that's going on in the US. I don't know why the US seems to be a bit of a trailer in this, but I would imagine that soon cities are going to see the tremendous value in being able to do this so that they can truly optimize, as I said, their urban development, economic development, and improve the well-being of their inhabitants and citizens. So that's my presentation for AI and energy today. So Anna, why don't I go back to you?
Thank you, Dale. You still have 1 minute to present, and there is a question that came from the audience, more a clarifying question with respect to digital twins. So I thought maybe you could quickly address that. So
Sure.
The question is whether, what is the purpose of that digital twin? And John Martin wonders, whether the purpose is to accurately represent systems for which no physical twin exists, or it is to calibrate the AI so that it can accurately predict future outcomes of the physical twins, or both.
It's, the first one can't exist because it wouldn't be a digital twin. A digital twin has to have a physical entity that it's matching up to. For instance, if I build a digital model of a process, say cash flow, dealing with some particular element of the economy, if there's no data that's coming from the actual physical entity back into the model in real time, and no information coming from the digital model back into the economy in real time, it's not a digital twin. All it is a digital model. If there's actual data coming in from the system into the model in real time, but nothing going back in real time, it's what's called a digital shadow. You've got a model that is receiving real-time information from the entities, and so you've got a view into that entity in real time, but you're not influencing the physical entity. It's when you've got that complete real-time link that it becomes a digital twin. The purpose of the digital twin is to understand precisely what is going on with the physical entity that it's twinning itself with at any moment in time. But more importantly, when it's done that, be able to project forward the state of that physical entity. Again, be it either a physical asset, a system, or even a person, forward in time to understand what could possibly happen to that entity given a change in its environment. Okay, let's say with the building, let's say you're projecting forward a change in weather. How would that ultimately end up impacting the energy usage in the building? These sorts of things. So it's used for both purposes, understanding the current state as well as projecting forward in time.
Thank you, Dale, for this clarification. Suzanne, now to you.
Great, thank you, Anna, and thank you everybody for participating today. I'm going to pull up my slides and then we'll get going. Okay, I am the CEO of Pecan Street, Inc. We are a not-for-profit research and development organization based down in Austin, and what we're primarily known for is a large amount of data that we collect on how homes use energy and other resources like water and natural gas. Our data is all collected from volunteer households like these, where we instrument those homes with a variety of sensors to collect very high fidelity, high granularity data. And in many cases, we're also able to incentivize the adoption of distributed energy technology like this neighborhood that you see here, which is one that we work in, where we've been able to work with our local utility and a number of the households within the community to get electric vehicles and solar installed. And that provides researchers with the data sets that they need to understand what are the management solutions that are going to be needed as we transition more and more quickly into a clean energy future that does rely on distributed energy resources. This is an example of the data that we collect. These are all direct measurements. None of these are aggregations or disaggregations of data points. And all of the data is made available for research purposes through our online data portal called Dataport. Pretty simple to understand.
Okay, no problem.
And we have also a database on our website of a couple of hundred peer-reviewed publications that have been made with this data, just as a way to continue to advance and coordinate on knowledge development in this sector. And I'm happy to be able to talk to this group today because as we transition more and more, as I was saying, to distributed energy resources, it's really flipping how we manage our grid onto its head. Whereas we have traditionally had central command over a relatively small number of large generation resources that are pretty reliable, predictable, and stable, and relatively reliable and predictable load profiles from the different industries that our utilities serve. we're now moving into a space where most of the innovation in the energy sector is happening on the grid edge. It's advances in consumer technology, it's charging infrastructure for electric vehicles, solar panels, but also advances in new kinds of distributed energy and home energy management, like Dale was touching on. And so we really need to understand a lot more now. And again, it's all the things that Dale talked about: behavioral economics, engineering, new systems and technologies, and where that gets married is with data. And we think AI is absolutely critical to enabling us to get to this clean energy future, because as we have an increasing number of generation resources coming online at the same time that we have extreme variability occurring and the loads that utilities have to serve, we need to have a platform where decisions are being made in real time to balance and optimize generation with demand. And AI lets us do that. But there are a number of ways that we need energy economists to engage in the space to let us get there. And this is just an example of some of the services that are being left on the table with distributed energy resources, because we don't have that real-time decision-making capability right now. And it's really important that we unlock these value propositions, because that's going to make rooftop solar panels and electric vehicles become a better ROI for the consumer. And that's how we're going to really accelerate adoption of these technologies. And so as we move to this very different, really radically different approach to grid management, we need to think about different models for intelligence, for how we manage all of this data and how we make decisions. And we think a really good model for that is the octopus. Whereas I think it's pretty good parallel to say that our traditional centralized grid management structure really follows a human intelligence model, where you have one brain, one data center that's collecting a lot of information from the nervous system and then making decisions and then sending those decisions back out. With an octopus, you have real-time decisions being made across its body, and it's a concept that scientists are calling embodied intelligence. It's been incorporated quite dramatically over the past couple of years into robotics development, and we hope also into grid management. And this video that you're watching just gives an example of how the octopus's body moves in a different way than its head does. They're not necessarily going in the same direction, but you can see that it still functions as one coherent organism. And that's because there are different decisions being made in different parts of that body. It's a physical system, and it has a very distributed neurology. And that's where we need our grid to go, and that's what AI enables. I'm going to kind of speed through these slides because I know you guys will have access to them if you want to dig into any of this information later. But again, this is actually a physical representation of how our grid should function to really optimize distributed energy resources, which again is critical to getting to the clean energy future that we know we need for climate mitigation, but also to unlock a lot of new economic opportunities for households around the country. And so the main challenge, the main reason that we don't have this real-time data integration occurring yet between households and our utility, there are good reasons for this. The first one is because of data security. Utilities are very heavily regulated around data and around access to the grid, and for good reason. You can see here with consumer data, there's been a number of high-profile cases where our information from our phones, from our computers, from websites and platforms that we use like Facebook, that data is not really protected in a lot of the ways that we just assumed it would be, that we don't own a lot of that information that really is information about our identity and our choices. This is just one example of how a third party was able to access locational data off of a phone for one of its reporters. This was a New York Times journalist who allowed this to happen. But everything that you could learn just by having access to that information about a single person and what kind of security risks that exposes. So this is a big challenge for utilities to overcome, but there's also a lot of benefit to opening up this kind of locational data. And we can see that in all the ways that locational data is really critical to our lives now and to the applications that we use very heavily and that a lot of us rely on, especially as we've all moved to distributed working environments for the most part around the world. So there's a lot of value proposition and there's a lot of challenges. And at this point in time, our perspective is that utilities aren't seeing enough of a value proposition with AI and with customer data and trying to figure out how do we integrate these data resources to spur them to overcome the regulatory and privacy and security challenges that we do need to tackle and that we need to tackle before we just open up all of our household data as well as our grid data to make this great clean energy, AI-driven future enabled. And that's one of the ways that we really hope energy economists will start to engage in this space, is helping us figure out what are those value propositions, how do we structure rates, how do we structure incentive programs for new kinds of technology that provide a broad societal benefit in a way that utilities can capture that value and help share it with their customers as well. This is one specific case study that I'm going to show. We have Texas' first grid-connected vehicle-to-grid charging system, which means it's a charger that provides power to your electric vehicle, but it also can use that vehicle just like a battery storage and pull power out of it to serve the grid, either at times that the grid needs to be stabilized or it needs to have more distributed generation available, or when prices are high and customers want to sell that power back and make a little bit of money off of their car. And these are some of the value propositions that we've been trying to test in partnership with our regional utility, Austin Energy. So as you can see, the technology is there for a lot of this. It's there for AI. AI is at a place where we need it to be to have transparency, to apply it to these great public sectors like electric utilities. We have the clean energy technology. We've got the integration technology. Customers are really starting to invest in these systems. But what we don't yet have are the economic solutions that really properly value these resources. Here in Texas, we have something called 4CP. It's 4 critical peak pricing events, where large purchasers of power from ERCOT, this is how their rates are set for the following year, is 4 days are analyzed, and you have a 4-hour window within each of those days to determine what is that purchaser, and our municipal utility is considered one of those large purchasers of power. What's their peak rate during this peak grid demand cycle? And then that sets your rate. So a higher user pays a higher rate. A lower user pays a lower rate. We were looking at one of the value propositions of vehicle to grid technology and distributed energy storage, helping to drive down the 4CP that Austin Energy would pay in the following year. And that was really successful, but it's just one example of how we need economists to really engage in this space to help engineers and technology developers get these solutions right. And also for research organizations like Pecan Street to understand what are the data sets that we need to be creating right now while we do all of these technology demonstrations and pilot programs to enable you to do that kind of analysis. Just another example with numbers and money. And that's it. Thank you, Anna.
Thank you, Suzanne. I appreciate it. The example with the octopus is a really great illustration. I don't see any questions with asking for clarification, so we'll move on to the next presentation. In our trip around the world, we have heard examples from Singapore, digital twins in Singapore. We've heard now example from the US, and now we are going to hear from Estonia, AI applications in Estonia. Kristjan, the floor is yours.
Anna, I will share my screen. Okay. So I expect you to see this screen, and I start from a little introduction to our small little country. So me and Dana are both from Estonia. So first, Estonia is a very small country. It only has 1.3 million residents living there. It's clean nature and digitally advanced society. So 51% of territory is forest land. And currently 98% of companies are established online. In recent parliamentary elections, 44% of votes were given digitally. And one more interesting aspect is that in recent PISA test, which is this education test around the world, we placed on first position in all 3 categories in Europe. So our education level is also very good at the moment. So what about Eesti Energia, where I work as a technology scout? Eesti Energia, or Enefit, our international name, it's a state-owned energy company. And we are active in the whole value chain, starting from mining, energy production, network services, and customer services. Traditionally, we have produced electricity a lot from oil shale. But due to CO2 tax in Europe, this isn't a very profitable thing anymore. And very fast we have moved towards renewables. So in first quarter 2020, Enefit actually produced 61% of electricity from renewables. And this is up from 25% in first quarter of 2019. One very interesting aspect, and it also comes into play due to our smallness or that we are so small country, 100% of households have smart meters. 94% of customer interactions in Enefit are done online, and this includes more than 90% of contracts. All are signed electronically via self-service. And why this is important, we see that Estonia and Enefit might be very good testbed for new energy applications. We are doing a lot ourselves. We are doing our best, but of course there might be some other interesting cases where, like, you are looking for a testbed, and it's definitely something to reach out towards us possibly as well. But now towards energy applications in Enefit. So we have done AI applications in many fields actually, but I want to share two which has, I think, some interesting tweaks to them that is more like novel compared to maybe just doing some statistical models. First, I want to talk about AI in distribution network. As I said, we have 100% of our distribution network covered with smart meters. And this has enabled some use cases which might not have been possible otherwise. First, predictive maintenance. The predictive maintenance that we are doing in the grid uses three data sources mainly. The first data source is this smart meter data. We have several years of this data. Then the second set is substations data. And the third set is historical data from field inspections. So, and this field inspections data is really important to get like labels for supervised learning tasks. So supervised learning is a field of machine learning where you try to map patterns, historical patterns of what has happened to what might happen. And so this is how we try to predict fault events by taking this historical truth and try to kind of predict the future from this. Now, the second interesting use case which have been possible is electricity theft detection. The main use case goes like this, that we aim to find patterns that defy physics. Because we have both smart meters data and we have substations data, then we can compare the two. And by comparing them, we can detect whether we see some kind of interesting things happening. For example, decreased voltage without increasing current. So the physics says that when we have the voltage decrease in certain household, then we should see the increase in current at the same time. But when we see a pattern where such a physics doesn't apply, then it might be a potential case for electricity theft. And currently we are detecting, this is more like this is very new project and we don't know the exact results. We are currently detecting roughly 500 to 1,000 theft cases per year. And we expect this kind of approach to increase this number. And the second use case of AI application that we have implemented is the chatbot or virtual agent. And this virtual agent is for solving our internal IT issues. So every day our IT department receives roughly 200 to 300 requests. And the main workflow for this virtual agent is as follows. Enefit employee sends an existing IT issue in free text format. And by free text, we just mean that something is written somewhere. Like, I have this issue with my computer, please solve it. And then virtual agent can do three things potentially. It can either solve the issue automatically by saying that, okay, I understand what you are aiming for and I'm able to solve it myself. Then the second option could be that it guides it toward the solution or sends the issue to human expert. And while chatbots themselves aren't like something that is like very novel anymore, like lots of companies are using them, then still one very interesting thing emerged from this initiative. And it was the emergence of a new job called bot trainer. So this was something completely novel. And this is something that we see probably more and more with new AI applications happening. The emergence of some new job positions. What does this bot trainer do? So the bot trainer aims to carry out his daily routine as follows, that he takes the historical or incoming IT issues and then tries to map the IT issues with what the person really wanted to do and what could have been the solution. And by giving this data to the AI model, then AI can get smarter and smarter and smarter with every day. So this is an interesting collaboration that is now happening in this one application where we have AI and its human trainer. And then one of the large fields that we are currently actively working and then probably all energy companies are working is the flexibility. And electric vehicles, flexibility and distributed energy assets. And I will use the electric vehicle as an example, distributed energy asset, because it has such a fun features as Suzanne also mentioned, that it can both kind of consume electricity, but it can in a way also produce electricity by sending electricity from battery to the grid. And while this flexibility is interesting, we really soon actually see that there are lots of different initiatives wanting to get a piece of this flexibility, starting from optimizing the charging cost. For example, that we have day-ahead energy price known and we want to optimize. Then the second initiative will be that we want to optimize grid investments, because grid really isn't built right now for such a large fleet of electric vehicles, which will maybe come in next 5 years. And maybe we can do something like this, that we reschedule the charging under some substations so that we don't need to make huge investment. We can replace it by just smart scheduling and paying people a little bit for this. Then, of course, home energy management. Electric vehicles can do a lot of things in home energy management, saving electricity while it's like cheap, and then providing electricity to home while it's expensive, and so on and so forth. And then also virtual power plant. Virtual power plant wants to get the flexibility and sell it to the frequency market, for example. And now the challenge emerges that many different initiatives are competing for the flexibility of one single asset, and this needs to be solved somehow. So first, we haven't solved the issue, but we are moving towards it with small steps. What we have done, we have approached these single initiatives. So regarding charging cost, optimizing the charging of electric vehicles so that the charging will take place with the cheapest price. We know day-ahead prices, and we know some kind of comfort patterns that the person have, and we can set some comfort patterns. And then it is pretty much optimization with linear or dynamic programming that is run once per 10 minutes, and we can do this. This is kind of a simple thing. But the future will move forward from here, and the future will move forward towards trying to orchestrate those different initiatives and to really try to give an answer of who can optimize at this time point. These are just 4 that I bring out here, but there are actually many more initiatives wanting to get a piece of this flexible asset. And there are 2 things that are happening that we have started to work and we see that are needed in order to make such a solution. First is a simulation, because we are talking about electric vehicles, but in Estonia, there aren't actually many electric vehicles at the moment still. But we see that in 5 years' time, there will be many. But it's a kind of this chicken and egg situation, right? That we know that something will come, but we don't have at the moment. So how can we do something to optimize it? And we try to solve it by simulating the existence of electric vehicles and simulating some profiles of users as well. So taxi driver, maybe a soccer mom, maybe somebody else, and try to create a large simulation where we maybe have like 50,000 electric vehicles. And then from the AI side, as I mentioned, optimizing single asset can be done with methodology that is familiar maybe with for economists as well, like or traditional like optimization, like linear or dynamic programming. But here we see that we probably have to go towards reinforcement learning. This is the set of algorithms that has been used to solve the games of Go and chess. Probably you have heard those nice use cases. And the reinforcement learning can handle large number of states and actions. And yes, this is something for a future work and more for inspiration for you. That was my last slide and my contact as well here.
Thank you, Kristjan. I would like to encourage the participants to use the Q&A option to ask the questions from the speakers. And I will go ahead and ask the first question from Kristjan. For Kristjan, that would be how to decide what AI initiatives are worth the cost. This is a question economists might be asking themselves.
Yes, the AI initiatives are kind of different from the traditional IT projects due to the fact that when making or procuring IT project, one defines functionalities and non-functional requirements, and the IT program is pretty much ready when these functional requirements have been satisfied, when the developer have developed these solutions. With AI, it's a little bit more trickier because before carrying out the AI initiative, we don't really know what is the value or how much accuracy the AI initiative is able to get. And it is very hard to kind of say how valuable this AI initiative is without really knowing like what will be the accuracy. So this is a little bit the fundamental question and maybe also towards economists to work on, that how to decide and how to model the value of AI in this situation where the outcome is probabilistic. So I don't have a good answer to that.
Thank you. There is a question about whether EVs will be assisting in renewables penetration due to them being batteries on wheels. And any of the panelists, feel free to take this question by raising your hand. Suzanne, would you like to address that?
Sure. Yes, we do see electric vehicles being a critical part of the distributed energy system, if I'm understanding the question correctly. in part because they are flexible supply with the advent of V2G technology, but they're also a flexible demand resource, so they can help serve as a power sink when needed. When we have a surplus of distributed energy online, for example, like in the state of California, it's estimated that last year California curtailed nearly 40% of its solar production capacity. So EVs let us better absorb that production that tends to happen in the middle of the day. And also in Texas, we have about 40% of our power generation capacity served by wind energy. And electric vehicles also let us absorb that power, which is a preferred power resource, by charging in the evenings and late at night when that resource is online. So I think they do serve really critically as a fundamental part of our distributed energy system going forward in both of those capacities, which makes them uniquely valuable as well.
There is a question about open source data to build AI models. Whether the panelists know any open repositories that can be used to train these AI models. Again, let's do the hand raising. If you know such repositories. I see Suzanne.
Can go again if nobody else has an answer. So as I mentioned, Pecan Street has a massive amount of data that we let researchers work with. It's over a petabyte of data, and we're currently in the process of building out some cloud computing resources that researchers can use as distributed servers, which we think will help unlock a lot of the value that big data enables with AI. And there's also a number of open data sets available through EIA here in the US, as well as NASA and other federal agencies like NOAA. And then there's a couple of very interesting independent efforts to get more data available in central repositories. One is called NILM-TK. NILM stands for non-intrusive load monitoring. So that's a lot of energy use data to try to create disaggregation algorithms and to model out energy demand profiles. And then another one is climate change AI. And that's just a good data resource and an interesting place to go to understand how AI is being used by researchers to try to tackle climate change.
Thank you, Suzanne, for these pointers. I also see that Dale has some ideas with respect to open data repositories.
Right, Anna. In many ways, a lot of data that you can find is from universities that they've gotten it from working in conjunction with various industries. And many times those universities post the data either on their own particular websites, or the research labs have set up GitHub accounts to make the data available. So if you do, some intelligent searching through GitHub websites, you will also find a lot of that data. I've found a lot of data regarding wind turbine generators that way, as some entities have put up data up there for you to use. So there's no tried and true method for finding it. It takes some significant detective work, but the data is out there. If not, then it's well worth it for you to look into establishing a relationship with an entity that produces that data, and working with them and being able to gain access to the data that way.
Thank you, Dale. Another question is about impacts of using AI and how to quantify it. As you know, economists love quantifying impacts. So have you come across any examples that specifically quantify the use, the impacts from using artificial intelligence or machine learning algorithms, and how many cents or per kilowatt hour it has the potential of saving? Or any other impacts you can think of, environmental, jobs.
This is Suzanne. I have not, but again, I think that speaks to the need for energy economists to really engage in this space. It's something that we've been interested in trying to do for a while at Pecan Street, but without economists on staff, we've been ill-equipped to carry out that kind of research project.
Got it. We're hearing a lot that the robots will come and take our jobs, but we don't have hard evidence yet, right? Dale,
And
am I seeing that you also want to address that?
yeah, there have been instances of where utilities have done proof of concept studies under the auspices of various state programs. Let's say in New York with New York State's REV initiative, revisiting the energy vision, or revising the energy vision, I should say, where there have been instances of where the impact of AI in terms of engaging in active demand response was tested out and was proven to have a significant impact on the cost of energy to the customer, as well as an impact on better management of the grid. The problem is, though, that having these programs in place, given current tariff structures. So getting the technology in place isn't just one of producing the technology and getting customers to adopt it. There has to be tariff revision. And that, in many cases, ends up being the true stumbling block. So a lot of negotiations have to be going on with regulators to change their views towards a lot of programs the utilities would be able to offer customers.
Thank you, Dale. We are on top of the hour. Thank you, everybody, for your insights, and the audience for participation and for questions. And I'm handing the rein back to Dave Williams of USAE.
Oh, thank you, Anna. And really, thank you to our distinguished panelists. This has been an outstanding webinar. I personally have learned quite a bit, and I'm very grateful for everyone's time and expertise. For all those listening, this webinar will be archived and on USAE's website in a matter of a few hours' time. If you're not a member of IAEE and USAE, we encourage you to join by visiting us at www.usae.org. Wherever you're located on this globe, we appreciate you listening. Thank you very much, and I officially close this webinar. Bye now.